Hello, this is Dylan Shang with the final sprint. I'll just use the checklist going down, but first let's start with the demo. Alright, so this is the first scene. As you can see, there's the terrain. Um, the texture on the terrain is a little off. I think that's because of the texture itself, and not a product of my calculations. But yeah, as you can see, the height map is working. Um, yep. All right. Next scene. Here's where everything is. All right. So I'll come if I need to. I'll come back to this and demonstrate for specific systems later. But here's just a general overview. Um, as you can see, the height map is working. Um, it's a different terrain from the last one. The collidable group has its own bounding box. I don't know. It's kind of hard to see because I made it black. But all of the spaceships have their own big collidable group bounding box, ABB. They all have their internal spheres, and then they have their separate. For now, right now, there's ABBs on the separate ships. The collidable groups can collide and then enable the bounding spheres to test. That's why they're turning green, and then things turn red when they're actually colliding. As you can see, the two ABBs are colliding with each other. Whatever, and yeah, that's that. And what else? The terrain, as you can see, it lights up blue when there's the ships over it, and that's per ship. And when when the bounding sphere collides with the terrain, both the terrain cells and the ship's bounding sphere turn green. And when the ABB hits the terrain cells ABB, both turn red, signaling a collision, as shown by the debug. And this works for all of them. Yep. Alright, let's start with the checklist then, with the old stuff. Alright, GAM object lifecycle. So the bullets are all getting recycled. Hold on, let me get back. Yeah. So the bullets are getting recycled. If I change scenes while the bullets are still there, the alarms are deregistered. Yeah, the alarms are deregistered. The bullets deconstructor or scene exit's called, and they recycle themselves back into the factory. Where is it? All right. What is this scene? Okay. I think we're done for the thing for now. So scene. Where is it? Here we go. Doesn't do much. It has just like last quarter. There's a bunch of managers. It doesn't do much except for create commands for the managers. The update is ordered, works. The draw manages the visualizer and the draw manager. The scene, yeah, I'm not sure what you want this to test, but everything, there's no crashes or anything, even with all these collisions and terrains and bullets and whatever, so I guess, I don't know if that's what you want, but moving on. Where is it? Camera manager. Yes, camera manager is a scene level. Where is the scene manager now? Camera manager is right here. It does define the default camera right here when it's constructed. It has a pointer The scene manager actually is in charge of deleting the camera once the scene ends, um, or the camera manager is deleted or whatever. Um, and it cleans up its memory. Yeah. The time manager, I think I'm doing that correctly. I'm not sure how to test that. There it is. GodCam, as you can see, GodCam, rotations and moving all around, zooming in and out. Alright. Alright, collision system. The class diagram. There we go. Alright, so this is packed. Alright, so the additions, I believe the additions are the terrain and the visualizer render commands. The collision volume takes care of a lot more stuff. The collision volumes, the ABB and the OBB are added. The collidable has a pointer to the to an internal B sphere. Collidable group has an internal ABB. Visualizers beefed up. Yeah, I think. Yeah. Okay. So that's the class diagram. User selected volume. That's yes. So in the collision volume, there is a volume type, and each collision volume has its own. Keeps track of that. And then that's determined in the collidable. When the user calls set collidable model, they pass in a volume type, where it's a switch, and it checks the type, and then creates a new collision volume based on that. And from the user's point of view, here it is. They just do that. They can set an like an OBB or bounding sphere or whatever, right there, and it'll work. Internal B sphere, yes. Where is it? There's internal B sphere. It is defined. It's created when the set collider model is made, and it's updated along with the collision volume that they set. And there's accessors for both of those. Right. No graphics objects. Yeah, there's no graphics objects. Main methods. Yeah, initialization from the game object, and accessors, and it updates the data, and it has the collision intersection tests here. So yeah, that's the collidable. Collision volume. What do we got? We got. I already showed the class diagram for the collision volume. For each volume. So, alright. So we got all these methods for intersection. The collision volume also keeps track. This is just for all these are for visualizer stuff, based on how I did the visualizer. These are all called during the collision tests. Change the visualizer color based on what's happening with it. So the separate collision volumes, they all have their own things. Bounding sphere has a center radius world. OBB has all of the necessary things, as well as the ABB. Unfortunately, I wasn't able to split up or parent the OBB and ABB to a bounding box, but I'm sure I'll get to that. Yeah, I'll get to that soon. So I don't think we changed the bounding sphere this quarter. So here's the ABB. Computes the data. like I said, I haven't gotten a chance to parent them both to the same thing, so this is basically the same. Um, yeah, it's got all the same accesses and whatever as OBB. Um, here's the compute data for the OEB. It's basically the same as the ABB, essentially. It gets the same accessors. And then this returns the matrix for the visualizer, I believe. What is this? Yes, the visualizer. That's how the visualizer renders things. Each thing has their own calculations in there. OBB intersection. So OBB intersection. So I use the second method, option 2, of the diagonals and the scale factors and the centers. The Oh yeah, I forgot to cover the visitor pattern, but the visitor pattern's right here. Double dispatch, and then it calls. Where does it call? It calls here. Just for the other intersect, and yeah, that it works with the visitor pattern. OBB intersection right. So in the math class, where is it? Math tools. OBB with OBB. Since I did this last minute, there might be some inaccuracies, but I didn't really notice them when I was testing with OBB versus OBB. I can test that now. Make this an OBB and make the cottage an OBB. Here's testing. So they're both OBBs. They go into there and they get collision. Let's see if we can zoom in. And it's pretty accurate. Yep. Yeah. So there's that. And here is the math for that. The intersect for OBB, it gets all the axes, checks the epsilon, and then there's OBB check, or passes in the axis in both the OBBs. Here's that method. The max projection distance is the distance between the centers, and here's that. Gets the dot product and does the calculation. That's the distance, and then the max projection for the half distances, or where is it? Here. For OVB, the half diagonal. It gets it via a accessor from the OBB, gets the dot product with all that, and then multiplies it by the scale factor. With the not separated ABB and OBB, I had to make just copies of the functions due to time. If I had time, it wouldn't be very hard to do that, but since I ran out of time, because I literally just did the OBB, I just completed OBBs earlier today, completely. So that's the best I can do right now. But yeah, they work. I guess I'll test the OBB and ABB as well. Here's the cottage. Switch it to ABB. And yeah. Kind of a mess of lines, but as you can see, it's working. Here, I'll make it easier and take out the extra things from the collidable group. I'll go to that later. Okay, so as you can see, the OBB is right there, and as it collides with the ABB, it triggers the collision, and I believe that should be... There's a little inaccuracy with the OBB and ABB because of the... Oh, yeah. Well, yeah. But the OBV versus OBB is much more accurate than the OBB versus ABB. As you can see, it's going off as it rotates. That's should be, yeah. Boom. All right. Anyway, the collidable groups. Let's go through those collidable groups. So has an internal ABB. It registers that internal BB with the visualizer. Here's the update. That's called. What is it called? It's called by the. That's called when in the collision tests commands whenever it needs to. So it's called. Where's the commands? It's called over here. Get internal ABB. This is an accessor, and it calls the update at the same time. Yep, both those. Related work. New command pattern to update group ABB from collision manager. I guess that's kind of what the command does. The test does. It's a command that updates it whenever it needs to check. It's kind of works. Collision manager. Where is the game object? Collision manager. Triggering collision group updates. This does that by going through the collision tests. Like I said, destructor with proper cleanup. I'll test that. Put a breakpoint in there. And when I change the scene, it triggers, and it should clean up 2. And yep. And then the scene re-goes back, and then if I do it again, it should clean up 2 more. Yep. Alright. So, yep. That works. Collision tests. The collision tests are not constant references, I believe. Yeah, they're just regular. Unfortunately, I wasn't able to have the time to fix that. Test should use tiered approach. Yes. So here it tests collision group with collision group, and then goes through the collection, and then it tests the uh, first collection first collidable group B spheres with the second collidable group, and if those go, it goes through the next iterator through the second collection, and then it tests that collection's bounding spheres with the first collection, and if that goes through, it tests the bounding sphere with the bounding sphere. Then if that goes through, it tests the individual collision volumes. And as you can see, these are for the visualizer to change the color of the when it's colliding or not. Self-type. Self-type is here. It works. Let's see. I have two things testing the self here. Go through new scene. As you can see, they're colliding smoothly by themselves without any of the other houses triggering. There's some sort of there's a bug with the visualizer going on right now, I guess, where the bounding spheres are not triggering, or they're not changing color. That happens sometimes. It's due to the overlapping of commands, or overlapping of calls on the colliding. But anyway, yeah. So there's that. There's the two. It tests the B sphere, and then it tests the two collidables, or the collision volumes. Then you test for terrain collision. I'll get to that when we go over terrain. Visualizer. Visualizer is up here. So the visualizer is a singleton. It has it keeps the graphics objects. It doesn't create new ones every time. Here, when it's created in the constructor, it just gets that and does it good. Renders all of the collision volumes. Renders the terrain, and then it has separate methods to highlight the terrain under game objects. One for at a point, and one for an area of it based on the bounding sphere. And there's a register for commands of a visualizer. Here's the implementation. So the delete, it deletes the graphics objects and clears the storage. This is a safeguard, but there's also another delete function for the storage. So here's the renders. All it does is gets the color that it should be default, and then sets the sphere to that if it's not colliding. If it is colliding, it'll get the colliding color from the collision commands, collision test commands, and set it to that instead. Gets these worlds. It's basically the same for both ABB, OBB, and bounding spheres. Rendering terrain. This renders the terrain cells. It's not an actual OBB. It's just a taking from the min and max corners of the cells, and then making the box off of that. Get to the highlighting later. So yeah, here's the register. It makes a new command here. Here's a new command. that takes the type of volume it is and then switches based on that to render the right thing. Processes the elements. This is processed in the draw of the scene, and then it clears the visualizer to test that the visualizer clears correctly. Every time the scene ends, it clears it. All of them. Oh, that's a lot. Yeah. And it does that again. Okay. Did I get all this? All render requests done by command pattern? Yep. No new gravity? Yep. Show bounding volumes. Show all bounding volumes. Yeah, that's the process elements, I believe. Additional tools. I did not use marker or lines for my OBB debugging process because I didn't really have time to set those up and figure those out. Others, I don't think there's any other different things. And I didn't get to colors either due to time. Math tool. We already got a look at it when we were going over collisions, but here, so 6 pairwise volume intersection. Yeah, there's all the collisions with the different things. Bounding sphere, ABB, ABB, etc., etc. And those all have their separate things. Bounding sphere versus bounding sphere, we don't need to go over that. ABB versus ABB, ABB check overlap is here, and it just gets the corners and checks them if they're if any of the points are overlapping in the other ABB. Let's see, bounding sphere to ABB clamps the point to the nearest to the bounding sphere, and then checks pointed to spec sphere, which is right here, which just checks if it's in the radius. And that's the same, basically the same for the OBB, except it has to get the center of the OBB. Already went over the intersects for the OBBs. So yeah, that's the math class, I think. Many support methods. Yeah, if I had the time to separate the OBB or combine the OBB and ABB, I would have done that. But unfortunately, I do have duplicate code because of it. I rushed it. Anyway, on to terrain. Let's see. This video is still going. Okay, good. Terrain. Where is it? Let's collapse these. Terrain. Here's the terrain object. Let's go to the header first. So it has all these data things. Row size is the total number of the cells in a row, and total cells is the total number of cells in the whole thing. Rest is self-explanatory. Cells data is the array of all of the terrain cells, and the highlighted area is changing based on whenever the user wants to call the visualizer to get the visualizer, or if the collision test needs it to get the cells underneath a game object. That's what the highlighted area is. And then it keeps track of a cell iterator used for collision tests. Creates the terrain model, saves the terrain model, various math operations for getting indexes. Um, computes the group ABB. That's for the highlighted area. It doesn't actually compute an ABB. It just gets the maximum and minimum area of the highlighted area, and then the get row and column I'll explain later. Yeah, accessors. These are for the user. Yeah, called by the user. This one is for a point, and this one is for an area. So here is the actual definition. When it's created, it creates the new graphics objects for terrain. Let's see. It's gets the scale. It sets up the cells once the model is created. Destructor deletes all the things that needed to be deleted. Alright, so here's the create terrain model. All of the things are, all of the data that's needed is initialized. Self-explanatory. The cells data is created as a new array of terrain cells. And then the vertexes are created here. I'm not going to go over that step by step. It'll take too long. It's already getting long. Tries. It goes through both rows and columns, and makes them based off that. And then here is where the cells data is filled up. It gets all of the cells, min and maxes. So it sets the min corner and sets the max corner of all of the cell data, the terrain cells. It also sets the x and y index, but I don't think I use those anywhere. And then it saves the terrain model with the function you gave us, and then it loads the model manager model. Oh yeah, I forgot. Oh, I'll get to that. Yeah, it loads the model manager with the model manager, and then it deletes the verts and tries. Here's the compute the group ABB. This is, like I said, not actually making an ABB. It's just getting the max and min corner of the area underneath the game object from the bounding sphere. Getting rows and columns. So this takes a vector and then it converts it into either a row or a column number based on that. Highlight cell, like I said, gets a point and then highlights the cell under that point. Usually the game object will have that, and gets the cell data index. So that's gets the index of the row and column. So it goes into the row and column, computes what index that is, and then goes into the cells data index to go through the visualizer to draw that, draw the fake ABB of the terrain cell. That's the computing the fake ABB, and then it goes through the area under that and gets the indexes for each of the terrain cells, and then renders them just like that, except for the area. This is used for collisions. I'll get to this later, but this is the iterator for the collisions. This just sets it up so it can work. Like I said, I'll get to that later. Let's see. What is this? Terrain object. Right, asset manager. Where is that? So the asset manager is over here. Basically the same as the model manager and the shader manager and etc. etc. They are singletons. I used a map because it's the same thing as the model manager and shader manager. It's served me well. We got the load terrain and get terrain, and it deletes. Yeah, so it loads here, loads all. It puts it all in there. It has a default path, which adds onto the height map file, which are in a separate height map file, and then it just saves it with a new terrain object into that map. And the delete, if you want me to test that, I'll do that. So it should delete 2, I think, because there's two different terrain assets. Oh, whoops, I forgot to do that. But yeah, so 1, 2, and it deletes both of them and ends. Good. Main methods, load get. Yeah, there's load get, delete. Delete is called when the scene is deleted. Default asset needed by engine. I do not have a default flat terrain due to time. Data. Right, this is back to the terrain object. Data. The vertices and triangles are deleted. Here. The few floats and int, yeah. Graphics object, yeah. Yeah, here. Data structure for each terrain cell. Alright, yeah. So terrain cells are just a normal class. It has the min corner, max corner, y index, x index, y index, and then the things for the colors for visualizer. And then it has a bunch of accessors. Many internal support methods. Yeah, many internal support methods with the get row column and accessors and whatever. I was not able to get to drawing a point on the terrain, projecting a point on the terrain, getting a height over of terrain or terrain normal, fortunately. Oh, yes, I should test that, yes. So here's the blue squares are under, rendered under the object. They follow, and then when the object goes off the terrain, it clamps it and makes sure that nothing weird happens. It just gets the thing, the two cells closest to the edge. I'm not sure if that's what you want, but it's how I have it right now. And yeah, it works for all of the edges. Yep. So switch this ABB. Terrain manager. That's scene level, yes. Um, where's the scene? Scene has the terrain manager right here. Scene terrain manager. Scene terrain manager is very simple. It's scene level. It's got a pointer to the current terrain. It sets the current terrain with the terrain, goes into the asset terrain manager and gets the terrain based on a key that the user gives. And then it has an accessor for the terrain. And then, yes. So how it sets the terrain is the user calls from the scene set terrain, gets a key. From here, the scene, this is like the only thing the scene does basically. It deregisters the draw if there is one for the terrain, and then it sets the terrain manager's pointer to the key, or it passes in the key to the terrain manager to get from the asset manager to actually set the pointer, and then it registers the draw of the terrain with the command system. And that is called right here, and it's simple. Set terrain, terrain level 1. Oh yeah, load resources. Here it is. Loads the terrains. They pass in a key. They pass in the file name, and yada yada. They pass in texture, which is loaded up here by the texture manager up here. And yep. Collision with terrain. Alright, yes. So here's a demonstration of the collision with terrain again. Alright, so as you can see, you can't really see. Okay, here. So here the blue cells are technically under the object because of that invisible ABB that's being drawn. And then, as you can see, the bounding sphere collides with this cell right here, so they both turn green. And the ABB, the collision volume of the ship collides with the ABB of this terrain over here, so they both turn red. And as you can see, as we go deeper in the terrain, it collides very nicely. And yeah. So getting to the command of that. Oh, I had a class diagram. I should have probably showed this at the beginning. Anyway, so here's the class diagram of the whole terrain system. So the scene has a class, scene level manager, scene terrain manager, and the terrain manager, asset terrain manager is a singleton. The scene terrain manager has a pointer to the current terrain object. The terrain object has a bunch of stuff. It has pointers to an iterator and a cell's data. Yeah, so that's the class diagram. What was I doing? Right. Collision commands. Terrain. So here's the command for collision test terrain. It gets the current terrain from the scene manager. It has a AABB, temporary AABB for testing. There's a for loop that goes through the collection. It computes the group AABB, the fake one, from the collection's bounding sphere. That is then put into a terrain cell of highlighted area, The highlighted area just gets an accessor from the train of this recently computed group AABB. And then the cell iterator goes through. So right, cell iterator. Where's that? Here. So here's the definition for the header for the cell iterator. It keeps track of current, beginning, and ending cells. Keeps track of the current row, the highlighted row size, which is like all of the cells under it. So if there was a 3x3, it'd be 2, I believe, and 2x2. And this row size is the total row size. So like 15 is what it would be. That's the size of how many cells are in a row. So the cell iterator constructor passes in 2 terrain cells, the beginning cell and the ending cell. It passes in the highlighted area underneath, and it passes in the total row size. And that's called back in the terrain object right here. Here. And it gives it all the data that it needs. Where is it? And then all of the operators are set with some extra things, get min, max, and min, and then the colliding on again for the visualizer. So here's the definition for that. Sets all the things. Sets the current row to the highlighted row size just for the iteration. And then it does this math operation when it's plus plus. Yeah. So it goes through. It's hold on. Yeah. So the beginning and end sets the a new cell to the beginning, and then that is checked here in the cell iterator. So the cell iterator. So yes, okay. So the test creates a cell iterator based on the train's set cell iterator, which is here. This is the set cell iterator. So it gets all the information from the train, and then returns it to the test. Right here. So that cell iterator has all the data from the train it needs to go through and iterate without having to do anything else. So it iterates. It checks. It computes the. What is it? It computes the cells, minimum and maximum corners, and then it checks if the it computes it, and then it stores it in that already stored AABB for collision purposes, and then it uses the actual AABB for a collision with the bounding sphere. And if that works, it goes through with the collision volume of the GAM object, and then it calls collision terrain of the GAM object if that goes through. Boop, boop, boo. These cells should be efficiently identified. Math constant time. Yes. There's no loops. There's just ifs in the iterator. Right here. The relevant cells should be returned as collection within an iterator. Yes. So that's what the cells are. getting it. Just a pointer. Just cycle through all relevant cells, yeah. For each cell, test AABB against collidable. Yeah. Bounding sphere first, then AABB. Yep, that's happening right here. Shows that the test is functional even when the collidable moves off any of the force. Okay, so I believe that works. Actually, I haven't tested that. Why are you taking so slow? Alright, so let's see. So it's going off. Yep, it's not colliding anymore, and it's colliding when it goes back on. Yep, so that works. Documentation. Okay, documentation. Yes, I did update the documentation. So with the beginners, I revisited the beginners to add loading in the terrains in the load all resources. And I think that's it. That's all I put in the beginners tutorial. But I added a new advanced mechanics tutorial, which includes the terrain and collisions, how to set them up. It has just an example scene where it sets the terrain over there and explains it up here, and it sets all the collision pairs and cells too, and that's also explained. Then it explains how to set up your game object with collisions in the scene entry and exit, and then oh yes, so here I explain the visualizer stuff as well as different collider models. I list them out and have links to the definitions of those. They just describe it. That's in the constructor where they actually set the set collider model with the type. Update the collision data, say. I note that you can use the visualizer to draw the highlighted terrain under the game object if you want, and then program in the collision. And I also put a bunch of things under a new tab called Useful Tools. These are all collision classes and things that might be useful for the user, including visualizer stuff. What else is there? Is anything else to note? I think that's yeah, clear explanation how to start a new game, yeah. Relevant information, collision, new terrain and all parameters. Yes. Where is terrain? Asset managers, terrain manager. So, yep, here's the description of all of the things they need to do to load the terrain. Demo, detailed comment for user accessible methods. Yeah, yep, yeah. Alright, so I think that's it. Yeah, so there's a lot of stuff I didn't do. I didn't have any time to go to a personal project, which really sucks, I know. And it's, yeah, it'll probably bring my day. I probably won't be getting credit for this class actually due to it. But yeah, that week when I was sick, that week and a half when I was just out from all my classes basically, it just ruined my schedule, and I just couldn't keep up with this class, and I just didn't have. I was spending too much time on the engine and didn't have time to work on my personal project, and I just could never start it because I was so far behind because of that week. What else? Yeah, there's a bunch of stuff that I didn't do because of the time. I got all of the main things done, mostly, for most of the part. Um, yeah, is rough. Is there anything? Yeah, no individual project. Let's just go over this one more time. Kaleido groups, visualizer, yeah. I think I covered all of it. Yeah, so that's it. Unfortunately, I don't think this will be enough, but I did my best. I this last week, I like I worked crazy. I got the entire terrain system done this week, as well as fixing my OBB to actually work in at least an acceptable fashion. But yeah, still probably won't be enough. Anyway, that's it. That concludes the final sprint, I guess.